All right. So we're not going to go over these necessarily because I feel like we've done this a lot in the beginning. Degrees to radians, radians to degrees, the coterminal angle. We know that. Um, yeah, and then the reference angle. We've also discussed about the reference angle. But one thing I wanna talk about is the terminal point. So I want to talk about what the terminal point is. So let's make a little definition. What is the terminal point? What does that represent? It's the coordinates of a point on the unit circle associated with a terminal side and the angle made with the positive x-axis. So that's what the terminal point is. It's just a coordinate, the coordinates of a point on the unit circle. So if you look at this, it says find the coordinates of the terminal point on the unit circle. So once we know that it's a unit circle, we know that the radius, right? We know the radius is 1 and the center of it is at 0, 0. And we want to find what the coordinates are of a point, x, y, that corresponds to an angle of 4 pi over 3. So if I take this point, which started from here in a way, right, from 0 degrees, and I go around the circle 4 pi over 3 radians, what would be my new coordinate? What would be my coordinates? So how do you go about this? Well, one way to interpret this is, again, drawing these right triangles here. So in a sense, this right triangle gives us a lot of information about the terminal point itself. One thing to remember always on the unit circle is that, so on the unit circle, always remember that x comma y is equal to cosine of the angle comma sine of the angle, because x is equal to cosine theta and y is equal to sine theta. We must know these two equations here. X equals cosine theta and y equals sine theta. So when I want to find x and when I'm trying to find y, I'm really trying to evaluate cosine of the angle and sine of the angle. In this case, my angle here is 4 pi over 3. And so therefore, the point x comma y that I have is really going to be cosine of 4 pi over 3 comma sine of 4 pi over 3. That's really what I'm trying to evaluate. I'm trying to find. So what I should do is I should do these individually and see what I get. So the first thing is, what is cosine of 4 pi over 3? So first of all, remember we talked about this last time. How do we evaluate trigonometric functions such as this? Of course, we did it more last time with degrees, but now we should be able to go from degrees to radians to degrees. So we have to figure out what quadrant I'm in. Well, obviously, this is in the third quadrant, right? So then you say, okay, I know it's in the third quadrant. If I'm in the third quadrant, then is cosine positive or negative? That's what I'm concerned about. So remember all students, right? All students take calculus. So we know cosine is positive in quadrants 1 and 4, but negative in quadrants 2 and 3. And since we're in the third quadrant, we should know that cosine is negative. And you can also think about that since x, remember, x is equal to cosine theta. All my x values on the left side of the y-axis, all my x values are negative. So henceforth, all my cosine values will be negative. So I know for a fact that I will have a negative somewhere. Okay, now once I've established the fact that it's a negative value because I'm in the third quadrant for cosine, then what I need to do is find the corresponding reference angle. Remember this, we have to find what the reference angle associated with theta. I'm gonna call this ref like this. So what is the reference angle of 4 pi over 3? Or how would I find the reference angle if my angle is in the third quadrant? What's the procedure? What's the little formula that I have to apply? Well, I do what? I do theta. I do theta minus pi. In this case, I get what? 4 pi over 3 minus pi. 4 pi over 3 minus 3 pi over 3 is equal to pi over 3. So my reference angle is pi over 3. So I'm really going to try to evaluate cosine of pi over 3. And again, this is because this is my reference angle, and we use our reference angles to evaluate cosine and sine of other angles, such as the one we were looking at, 4 pi over 3. And then we go look at cosine of pi over 3, and we should know the value of cosine for this angle. Cosine of pi over 3, same thing as saying cosine of 60 degrees. And cosine of 60 degrees is negative 1/2. So my x-coordinate is negative 1/2. That's the x-coordinate of the terminal point. So now I've established that it's negative 1/2. And now the second thing I need to figure out is called the y-coordinate, which is sine of 4 pi over 3. And I'm going to apply the same kind of reasoning here, right? I know already that this is in the third quadrant. I know all students take calculus, this little mnemonic device that helps me remember what's positive and where's negative. Sine is negative again in the third quadrant because the y values are also negative in the third quadrant, and sine represents the y values. So then we know that we're going to have a negative as well. And 4 pi over 3, we already know the reference angle to that is pi over 3. So we're going to evaluate sine 4 pi over 3 by first finding negative sine of pi over 3. So sine of pi over 3, we've discussed that before in the previous lecture, what sine of 60 degrees is. It's going to be negative rad 3 over 2. And that's how you find the terminal point. You're evaluating the values of angles and utilizing your information, your knowledge of where something's positive and negative, where a trig ratio is positive or negative, according to the quadrants, and then you find a reference angle to find the value of what cosine and sine would be. So any questions about the terminal point? Any questions? Okay, no questions. So let me do one more example here underneath this. So find the coordinates of the terminal point x comma y on the unit circle that corresponds to theta, and I'm going to give you Let's do 7 pi, no, 11 pi over 6. So drawing the unit circle is very helpful, just to give you a visualization of what's happening. So I got my y value, got my x value. So I have my unit circle and my radius is 1, and my angle associated with the point is 11 pi over 6. 11 pi over 6 is equivalent to saying 330 degrees. So it's as if I'm moving from this point here, 0 degrees, all the way around and almost making it completely around, but I am 30 degrees away from making a full revolution. So I'm going to have something that looks like this here. So I draw a little line here, boom. And then I have my point, x comma y, and this is my angle here, theta. This is theta. So theta is 11 pi over 6. And I want to find my terminal point. I want to know what the coordinates of my terminal point are. So I want to know x comma y, but since I'm on the unit circle, I know for a fact that x is the same thing as saying cosine of the angle, and y is the same thing as saying sine of my angle. And so what is my angle here? It's 11 pi over 6. So cosine of 11 pi over 6, comma sine of 11 pi over 6. And then, of course, I can do them individually, right? This is my first coordinate. This is my second coordinate. So what does my first coordinate say? Cosine of 11 pi over 6. Well, first of all, I'm in the what quadrant? I'm in quadrant number 4. So I know for a fact I'm in quadrant number 4, and I know cosine will be positive because I'm in the 4th quadrant. All my x values are positive in the 1st and 4th quadrants. 4th quadrant. So then now I know that's positive, and all I have to worry about is the reference angle. What is the reference angle? Like we mentioned before, it's the angle that's positive and acute, that's made between the terminal side and the x-axis. In this case, the reference angle is pi over 6. So I'm evaluating cosine at pi over 6. I'm asking myself, what is cosine of 30 degrees? And we have that table that we've done before, and we know that's going to be rad 3 over 2. So cosine is rad 3 over 2, which means my x value is rad 3 over 2. Now, let's look at the second coordinate, which is sine of 11 pi over 6. Well, what do we know again? Quadrant 4. Sine is negative in quadrant 4. So therefore, I must have a negative associated with sine. And I'm taking sine of the reference angle pi over 6. What is pi over 6 for sine? Sine of pi over 6, sine of 30 degrees is a half. So then I got negative a half. And this will be the coordinates of my terminal point. It's rad 3 over 2, comma negative a half. So this idea of finding the terminal point is building upon what we did right before the end of last class, which was to find how to evaluate trigonometric expressions such as this. Now we're combining two of them, cosine and sine. And we're finding where it is in the 4th quadrant, 3rd quadrant, what quadrant your terminal side is in. And based upon that, you're able to tell what the positive or negative sign, and then you use the reference angle to find the values of those angles themselves. So that's how you find the terminal point, the coordinates on the unit circle. Okay. So this is something we've done before, right? To find the 6 trigonometric ratios. In this diagram here, we have a right triangle, and we're given the opposite side of theta. Oh, yeah, I just saw. Thank you, Chen, for answering Prab's question. Yes, so sine is negative because um, in this case, in this example, because the y values are negative and the y value is represented by sine. And we'll see more a little bit later how the unit circle, understanding the unit circle really gives us, the theory behind most of the trig. If you understand the unit circle, then a lot of trig will make sense to you. If you don't, then it's going to take a little bit longer. Um, but we'll see a little bit later how the unit circle is, like the involvement that the unit circle has with the rest of trigonometry. And so here we have a right triangle whose opposite side to theta is 10 and whose adjacent side to theta is 24. And I want to find sine of this angle, right? So I want to find, for sine, I need to find what? Opposite over hypotenuse. So the hypotenuse is the unknown value here, but I have a Pythagorean theorem that I can apply to find that missing side. Or, if you guys remember, I talked about those Pythagorean triples. If you notice, this is 5 times 2, and this is 12 times 2. And remember one of the most basic Pythagorean triples? Is 3, 4, 5. We talked about this one. 3 squared plus 4 squared. So 9 plus 16 equals 5 squared, 25. Now remember, if we double everything, or in this case, yeah, that's one of them. But this is not the root actually. This is one of them. But the one I'm considering for this one is 5, 12, 13. This is the next common one. Remember this? So if you notice, this is the root, right? These are the roots. These are like roots of Pythagorean theorem. And the one that we're going to be considering is this one. Why? Because if I double everything here, what do I get? If I multiply by 2, multiply by 2, multiply by 2, I get what? I get 10, 24, 26. So I know this is going to be 26 for a fact. And then from here on, finding everything should be pretty straightforward, right? Opposite over hypotenuse. So I got 10 over 26, which really reduces to 5 over 13. And then once I know this, I know cosecant, which is just a reciprocal, 13 over 5. What's cosine? Cosine is the adjacent side, which is 24 over 26. But if I reduce it, I get 12 over 13. If I know cosine, then I know secant, 13 over 12. Tangent, opposite of hypotenuse, 10 over 24. This equals what? 5 over 12. Then the cotangent is 12 over 5. So yeah, we've done something like this before, but we're just given a right triangle in this case. We can use a Pythagorean identity triple or the Pythagorean identities, the Pythagorean triples that we've known from the beginning of this trig unit. We should be able to recognize them if you see the numbers that are associated with one of the roots. So knowing the roots helps a lot, because then you can just circumvent the whole usage of Pythagorean theorem. Okay. Okay. So we've talked about a lot about trig with respect to angles and the ratios. I know the next topic is the graphs, which is what we're going to get into. But before we do that, I want to talk about something called identities. So these are called fundamental identities. And again, we're going to start this stuff off with the unit circle. The unit circle is fundamental. So if we go back to the unit circle, So if we go to the unit circle, remember we mentioned about the equation. What's the equation of the unit circle? X squared plus y squared equals 1. So with trig, I do admit there is more memorization involved or recall that's involved. You have to remember certain things again and again, such as the reference angles. You should remember them, recall them. The values of those reference angles. And there's going to be quite a number of formulas for trig that will pop out here and there. Of course, one of these equations you should know prior to this semester, which is the equation of the unit of a circle, and in this case, a unit circle is x squared plus y squared equals 1. And what do we figure out when we have a certain point on the unit circle, right? We just talked about the terminal point, theta. So we know that x has to equal cosine of theta, and that y has to equal sine of theta. And so this is where trig and I guess you can call it coordinate geometry come together. Well, since we know that this equation of the circle is given by x squared plus y squared equals 1, and we know that x equals cosine theta, y equals sine theta, so what we could do is plug in or substitute x for cosine and y for sine, and you get cosine theta, you get this squared plus sine theta. This is squared as well, and this equals 1. And what we're going to do is, oh, pardon me, Felipe, what were the answers for what, the previous one, number 5? Well, it's right here. It's 5 over 13, right? Then 13 over 5, 12 over 13, 13 over 12, 12 over 5, and 5 over 12, like this. Okay. So guys, the important thing here is that x plus y squared equals 1. This is something that we know without trig. The moment we have this now, so this relationship between the x and y values and cosine and sine, you can now create like this new equation where now we're relating the sine and cosine of angles to one another. And what we've noticed is that cosine of theta, whatever that is, whatever theta that is, it doesn't matter. Any theta, as long as these thetas here are the same, cosine, if you square that angle, if you square the value of cosine of the angle plus squaring the value of sine of the angle, it will always equal 1. And that's called the Pythagorean identity. And the notation for this, we're not going to write cosine theta parentheses squared. This is just me literally substituting in the values directly. But the notation, the proper or the conventional notation for squaring a trig ratio or a trig function is the following. You put the squared in between cosine and theta. And you could do the same thing for sine. So again, this is just notationally what it means. It means that you're squaring cosine of theta. And this, my friends, is the well-known Pythagorean identity. An identity is something that is 1000% true. It's a true equation. And it's true irrespective of whatever angle you plug in. So let's see this. If this is true, then for example, if I do cosine of pi over 6 squared plus sine of pi over 6 squared, should this equal 1? Well, then what's cosine of pi over 6? Cosine of 30 degrees? It's rad 3 over 2. And of course, I am what? Squaring that. And then sine of pi over 6 is a half. And I'm squaring that as well. But then when you square rad 3 over 2, you get 3 over 4. And when you square 1/2, you get a fourth. And indeed, you get 4 over 4, which is 1. So this is just a little example of how the Pythagorean theorem, the Pythagorean identity holds true. And this is not just for this. This does not only just work for this angle. It works for any angle. You give me any angle, I don't care what it is. You plug it into this equation, and it will always add up to 1. Always. This is the Pythagorean identity. And let me just say that this is like the this is like the source of the rest of the formulas that you'll come across right here. Cosine squared theta plus sine squared theta equals 1. If you know this, then you can figure out a few more formulas as well. So this is a big one, right? That you should know. This is the one that you should know, and you probably will remember very easily because it's kind of in tune with Pythagorean theorem, with the unit circle. It's right there. So from this one, what you can do is you can figure out other formulas for cosine and sine. For example, from here you can say that cosine squared theta equals 1 minus sine squared theta. So now you can find an equation for cosine in a way. If you know sine, you should be able to find cosine, and vice versa. If you know cosine, you should be able to find sine. Right? So you see how we got this? We got this just by looking at the Pythagorean identity and subtracting sine squared theta on both sides. You would get cosine squared theta. And if you want to get sine squared theta by itself, you would subtract cosine squared theta and you get 1 minus cosine squared theta. So these will sometimes appear again. But again, these are fundamental identities. Fundamental. So cosine squared theta plus sine squared theta equals 1. And then from there, we have cosine squared theta equals 1 minus sine squared theta. Sine squared theta equals 1 minus cosine squared theta. Okay, and then I'll give you 2 more of these. So here we have, so if I go back to the Pythagorean identity, cosine squared plus sine squared equals 1, right? And if I divide everything, for example, by cosine squared theta, I get a new identity. What is my identity? Well, cosine squared theta over cosine squared theta is 1. Sine squared theta over cosine squared theta, if you take this a little bit, you can write this as sine theta over cosine theta parentheses squared. Sine theta over cosine theta is tan theta. So you can write this as tangent squared theta. And if you've got 1 over cosine squared theta, then you can write this as secant squared theta. And now this is another Pythagorean, well, this is another identity, trig identity, that comes from the Pythagorean identity. You see that? So if I divided everything by cosine squared, I get this new relationship between tangent and secant. So it's all about finding the relationships between these trig identity, these trig ratios or functions. So cosine and sine are related in this manner. Tangent and secant are related in this manner. And there's one more, that if I take the same identity, Pythagorean identity, cosine squared theta plus sine squared theta equals 1. Instead of dividing everything by cosine squared, I've divided everything by sine squared. I get another one. So what do I get? Well, if I get cosine squared theta over sine squared theta, I can rewrite this as cosine theta over sine theta squared. But cosine theta over sine theta is the reciprocal of sine over cosine theta, which means it's a reciprocal of tangent. So this is going to be called cotangent theta squared. And so I got cotangent squared theta, right? And then plus 1, which is because sine squared divided by itself is 1, and that will equal 1 over sine squared theta, which is cosecant squared. So these identities stem from, so I should write that, these trigonometric identities stem from the Pythagorean identity. Okay, so in a sense, if you know cosine squared theta plus sine squared theta equals 1, if you know that, you should know the rest of these. Because it comes right after it. It comes right from it. Okay. So for example, I can use this information to find the rest of the points if I'm given one. So for example, with this, I can say we did something like this before, but let's say if I have so it says find the values of all 6 trig ratios given that. So given that sine of theta is -1/4 and secant of that same angle is less than 0. So we've done something like this, right? Where in the last lecture, and we drew out the unit circle and all that, but we don't necessarily need that now that we have the Pythagorean identity and all the other identities that stem from it. So for example, I know sine already. So if I know sine, so these are the 6 trig ratios, right? So I know sine of the angle. If I know sine of the angle, I already know it's -1/4. And then I have to find cosine of the angle. And then I have to find tangent of the angle. And once I know those, then I know the reciprocal ones, right? For example, this would be cosecant theta, which will be equal to -4/1, which is just -4. Okay. Whoops, this should be 4. And then 5 should be secant theta. And then 6 should be cotangent of theta. Now, I want to know what cosine of theta is. Cosine of theta. But now, instead of drawing everything and like creating the right triangle and all that, I can just find what cosine theta is using the identity cosine squared theta is equal to 1 minus sine squared theta. 1 minus sine squared theta. So this is 1 minus, and this is -1/4 squared. You see that? Because I'm plugging in sine theta. I know what sine theta is. It's -1/4. So to find cosine squared theta, I do 1 minus sine squared theta. So then -1/4 squared will equal what? 1 minus 1/16. And 1 minus the 16th is 15/16. So cosine squared theta is 15/16. But I'm not trying to find cosine squared. I'm trying to find just cosine. So then obviously what I need to do is take the square root on both sides. So when I take the square root of something squared, remember, there's always going to be a plus or minus, right? So I'm going to have either the square root of 15 over 16, which is really the square root of 15 over the square root of 16, which really is the square root of 15 over 4. Or I'm going to have the same thing, just the negative version of it. Now, how do I know what sign is associated with cosine, whether it be positive or negative rad 15 over 4? Well, I have to establish, obviously, what quadrant the angle is in. So this is where we do where we deduce from the information that's given. So this piece of information, sine theta equals negative 1/4, causes me to deduce that the angle must be in the quadrants where sine is negative. And where is sine negative? Sine is negative in quadrant 3 and quadrant 4. That's where it's negative. And then where is secant? Also less than 0, which means negative. Well, that's when cosine is negative, and cosine is negative in quadrants 2 and quadrants 3. So in order for both of these statements to be true, they must be in the same quadrant. So that means that the quadrant must be quadrant 3. So angle is in, theta is in quadrant 3. So theta is in. So if I'm in quadrant 3, cosine is also negative. So then the correct value for cosine theta should be negative rad 15 over 4. It should be. And then once I know cosine is negative, then I know secant of theta is also negative, but the reciprocal rad 4 over 15. If you multiply up and down by rad 15 to rationalize the denominator, I get it's negative 4 rad 15 over 15. So these are my ratios so far, the values of my trig ratio so far. And then lastly, how do you get tangent? Remember tangent? Tangent of theta is really sine over cosine. So if I know sine and cosine, then I know tangent immediately. Sine is what? Negative 1/4. And cosine is negative rad 15 over 4. What do you do when you have a fraction divided by a fraction? You keep changing, flip. So this is negative 1/4 multiplied by negative 4 over rad 15. The 4's are canceled. The negatives become positive. So this becomes 1 over rad 15. And if you multiply top and bottom to rationalize the 15, rad 15, you get rad 15 over 15. And so that's going to be the tangent value. So it's rad 15 over 15. And cotangent, what is cotangent? It's just going to be the reciprocal, right? The reciprocal is 15 over rad 15. And if you reduce that, you get rad 15. Okay, so this is just an example of how we can find a given one ratio, trig ratio, and one extra piece of information to give us the angle, I can figure out the rest of the 6 trig ratios using the Pythagorean identity and the identities that stem from the Pythagorean identity. So that's going to be a good way to find the rest of the ratios without having to draw anything, without having to actually create the right triangles. You don't need it because you have these identities now. Okay. Okay, so we've done quite a number of things here. All right, so now Yeah, so this idea here comes up again and again. Once I give you one angle, once I give you one trig ratio, give me the rest of them. This appears again and again. So again, this method here is done without using a right triangle. And now I'm going to do the same thing, but with a right triangle, just to give you again the idea. So uh, find the rest of the trig ratios. Find the 6 trig ratios. Given that um, tangent of theta, in this case, tangent of theta is 5/6. So in order to do this, I'm going to construct a right triangle. So if I construct this right triangle, I know the opposite side will be 5, this will be 6. So I have to figure out the missing side. Something similar to what we've just done, right? It's just that these numbers here are not Pythagorean triples. So we're going to get something here that is a radical for the most part. So this will be 5 squared plus 6 squared equals x squared. 5 squared is 25, 6 squared is 36. That equals x squared. If you add 25 to 36, you get 61. So this equals 61, which means that x is equal to the square root of 61. So this is equal to square root of 61. And then once I have this, I have everything, right? I should get sine theta. I should be able to get cosine theta. I already have tangent theta. It's 5/6. So then I immediately know cotangent of theta is 6/5. Cosine is going to be equal to 6 over the square root of 61. Sine is going to be equal to 5 over the square root of 61. If I know these, then I also know the reciprocals. So cosecant of theta is rad 61/5. And secant of theta is equal to rad 61/6. And cotangent of theta is 6/5, which we knew. And if you want to rewrite this using rational denominators, then you multiply by rad 61 on the numerator and denominator, and you get 5 rad 61/61. And the same thing happens here. This becomes 6 rad 61/61 when you rationalize the denominator. Okay. Okay, and so we're gonna hopefully end up with the graphs of trig functions, which is the very next thing. But before we get into that, I want to talk more about right triangles. And what we have to get good at is finding the unknown side of a right triangle, finding the unknown side of right triangles. So I would say one of the main benefits of trigonometry is this idea of finding unknown sides. If you know certain angles and sides, you can find the unknown ones. So example, if I have a right triangle, I know the angle that's made here is 30 degrees. And this is an unknown side, and this is 25. Well, we should know what these are given the special right triangle, right? But we can talk about this now utilizing trig. So what trig ratio relates the angle theta 30 degrees with x and 25. So which trig ratio is associated with this? And Chen says sine. That's right. So which trig ratio relates the quantities in the triangle together? So again, this is going to be my theta. And opposite theta will be the opposite side, which is x. And this is the hypotenuse. So then obviously opposite over hypotenuse, it makes sense to use sine. And then what do we know? We know that sine of my angle 30 degrees, right? Sine of the angle is opposite over hypotenuse. So this would be sine of 30 degrees. You know what? I'm going to write this as theta. So sine of theta equals opposite of hypotenuse, which means that sine of 30 degrees is equal to x over 25. But then I'm trying to solve for x, right? I want to find x. That's really what we're trying to do, find x. So then how do I find x? I multiply both sides by 25. 25's cancel. And I'm left with x equals 25 sine of 30 degrees. That is what x equals. And because 30 degrees is a reference angle that I know that 25 is going to be multiplied by a half. Or in other words, it's going to equal 25 over 2, which equals 12.5. So I know for a fact that x, the missing side, is 12.5. Now, we could have also figured that out if we knew 30, 60, 90 triangles. So it's almost like expected to get what we get. But what if we have triangles that are not the typical angles that we know, that have the typical angles that we know? Like, for example, what if it's not 30 degrees, it's not 60 degrees, it's not 45 degrees? Those angles are the ones that we know for a fact because of the special right triangles. But what if we don't have a special right triangle? What if we just have a simple triangle? For example, what if I get this? Another right triangle. In this case, I have theta. Sorry, theta is 36 degrees. This is 36 degrees. This is 12. And this is x. So I want to find x, right? That's what I'm trying to find. Find the missing side, x. So what trig ratio relates all the quantities here? So which trig ratio relates everything together? So what do we have? We have theta. We have adjacent side, and we have the opposite side. And Tiffany, correct. The trig ratio that has the opposite over the adjacent is tangent. So we know that tangent of theta is opposite over adjacent. What is theta in this case? It's 36 degrees. So tangent of 36 degrees, what does that equal? The opposite side, which is what? 12, and the adjacent side, which is what? X. So you see, I have this ratio, this connection here. 12 over x, that equals tangent of 36. And again, what is it that I'm looking for? I'm looking for x. That's what I'm looking for. The problem is x is now what? In the denominator. So why don't we multiply both sides by x? When we do that, the x's here are canceled out. I'm left with 12, and I'm left with x multiplied by tangent of 36 degrees. Now I'm not going to find what tangent 36 degrees is yet. I'm going to still solve for x, right? I still want to get x by itself. So then what should I do? I should divide both sides by tangent of 36. And then tangents here are canceled out, whatever that would be. And I get that x is equal to 12 divided by tangent of 36 degrees. And now this is when you can use your calculator. Your calculator should have a trig function involved. And you just have to be mindful of, if you have a TI-84 or 83, you have to be mindful of the mode, or your calculator mode. So you have to go to mode in your calculator. There's a button that says mode. And then when you go to mode, see, I should be able to pull it up. Let's see. Okay, so let me share with you the calculator, the emulator that I have. So if I want to calculate, for example, tangent of 36, right? So I'm going to go to mode, and I'm going to go to where it says radian, and I'm going to switch it from radian to degree, because now my angles are in degrees. So then I do second quit. Then I go and I want to find what x equals, right? Which is 12 over tangent of 36. So then I can create this little fraction here, and I'd say this is 12. And the bottom will be tangent of 36 degrees. And when I press enter, I get a decimal. So x here would be 16.5165 ... All right, so make sure you are in the correct mode. Whenever you find a trig function, make sure you know what mode you're in, and that depends upon what the angle measure is. If the angle is in degrees, make sure you're in degree mode. If the angle measure is in radians, make sure you're in radian mode. Okay, so that's how we use our calculator to figure out the values of trig functions where the angle is not something that we know. 36 degrees, we don't have the information behind that. The way we do for 30 degrees, for 45 degrees, for 60 degrees. But our calculator does that work. And so because of that, this is actually very useful. It could be very useful. Okay. All right. So why don't we do one with radians, where you have an angle here that has radians in it. So I have a right triangle, and my angle that I'm interested in is pi over 5. You can find what that is in degrees. If you do 180 divided by 5, there's also 36 degrees here, but it's pi over 5. And the side here is 106. Now, what we're gonna do is we're gonna do what's called solving a right triangle. And what that means is find all missing quantities. Find all missing quantities, both sides and angles. So I am missing this side here. I don't know what this side is. And I'm also missing this side here. And I also am missing this angle here. So why don't we find the angle first? How do we find that missing angle? Well, we know what triangles, the angles add up to in a triangle, right? It's 90. It's so we have 90 already, right? Do we use radian or degree? Use tan or sec. So in this case, we're just gonna stick with radians, okay? Just to show you that you can still do this just if you have radians. So this is in radians. I want radians. I know that the sum of the angles in a triangle all add up to 180 degrees. So I know this angle is already 90, which means that these angles have to add up to 90. So then I know that theta, which is pi over 5, plus this missing angle must equal 90 degrees, but of course 90 degrees isn't degrees. I want radians. 90 degrees in radians is pi over 2. So I know this equals pi over 2. So then to find out what the missing angle is, I subtract by pi over 5. And then question mark equals pi over 2 minus pi over 5. Make them the same denominator. So what do I have to do? Multiply by 2 on both top and bottom. Multiply by 5 top and bottom. And I get 5 pi over 10 minus 2 pi over 10. Subtract the numerator now that my denominators are the same. And I get 3 pi over 10. So this angle here is 3 pi over 10. So I found it. Usually that's the easy part because there's not much mathematics here that's required. Now I want to find, let's call this A and let's call this C. So I want to find A and C. Now to find A and C, you have to, it's just, I guess we could just stick with the original theta, right? This is our original angle here. So I'm gonna call this here theta. And then I'm gonna see how is theta related to 106 to A and to C. So theta is pi over 5. 106 is opposite theta. So I'm gonna call this opposite. A is adjacent to theta, and C is the hypotenuse. So to find the adjacent side, knowing the opposite side, I have to use what? So to find A, use what? Use tangent. Tangent of theta because I know the opposite side over the missing adjacent side. So this will be tangent of pi over 5. This equals 106 over A. I want to solve for A, so I do very similar to what we did in the previous example. Multiply by A on both sides, right? The A's here cancel, boom. And then I'm left with tangent, so I'm going to divide by tangent of pi over 5 on both sides. So these tangents here go away. And I'm left with what? I'm left with A is equal to 106 divided by tangent of pi over 5. So what is that going to equal? Well, let me use my calculator. You need a calculator for these type of questions. So then I'm going to say this is what? 106. So here I have my little fraction. 106. And that's going to be all over tangent. Now make sure you're in the correct mode. I am not in degree mode anymore. I'm in radian mode. So press enter for radian. And then I go back to where I am supposed to be. And I do tangent of pi. So I do second pi divided by 5 parentheses. And so this is what I'm looking for. And when I press enter, I get 145.896. So 145.896. See that? So my A value is 109.896. So I found my A value. So let me just erase this here and let me just fill that in with 145.896. And of course, this is just an approximation. The decimal expansion continues. And so we found the adjacent side. Now, how do I find the hypotenuse knowing the opposite side, opposite of hypotenuse? So to find C, use what? Use sine of theta, because I know the opposite over the hypotenuse. And again, the sine will be what? Pi over 5. This equals 106 over the C value, which is unknown. To find that C value, multiply both sides by C. These cancel here. You divide the sine over pi over 5 over sine over pi over 5. The sines cancel as well, and I get C is equal to 106 over sine of pi over 5. So we do the same exact thing. We go back to our calculator and we do 106, 106, and one too many sixes, and then you divide by sine of, let me see if this works as well. Yeah, sine of second asterisk here, pi divided by 5. Close parentheses, and then boom. And you get 89. That you get a strange fraction there. So let me see if I can get the, let me see, mode. Let me go to decimal. Yeah, so I get 180. Yeah. Okay, good. So you guys got it as well. So I got 180.3 as well. Good. So now you can put that as your value for C, 180.337 dot 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 dot. So there we go. We are able to figure out missing sides of a right triangle if I know one angle and one side, because now I have the connections between the unknown quantities and the known quantities, using the trig ratios and using our calculator to figure out those missing sides or angles. So hopefully you start to see like how this could be very helpful, especially when we talk about engineering or anything that has to do with like buildings, anything that has to do with distance. Trig becomes an essential aspect of it, because we always want to find an incline of some sort, a decline of some sort with an angle. We want to be able to measure quantities, right? So trig is essential for that, for those kinds of endeavors. And let's see this. So of course, things like this can get a bit more complicated. What if I get two right triangles now, and this is 100, this is 30 degrees, and this is 60 degrees, and I'm trying to figure out this side here. What if I want to find x? I want to find x, and I'm given two right triangles, right? These are right. So I have one right triangle here, and I got another right triangle here. And I'm trying to figure out what is this entire side here. So this is when, your problem solving skills have to now come into play. What do we notice? X here is not a side of a single triangle. It's kind of combined, it's a combination of two sides, right? So you got one side of this right triangle and you got another side of this right triangle. And when you add them up, you get what X is. So then it would make sense to kind of decompose X as two components, A and B. So this is going to be my A value here. This is going to be my B value. Again, these letters here, I can choose any two letters, but A and B just feels right for this. So I want to find A first. To find A, so X is really going to be equal to what? A plus B. So I need to find what A is. So find A. What is A? Well, what is A? A here is going to be the adjacent side to the given angle 60. And this will be the opposite, 100. So it makes sense to do what? It makes sense to say tangent of 60 degrees equals opposite over adjacent. You see that? So now I can find A. Multiply A on both sides. A's cancel. And I'm left with A multiplied by tangent of 60 degrees equals 100. And now this doesn't have to be that hard because tangent of 60, I don't need a calculator for that. I should know what tangent of 60 is since I know what sine and cosine of 60 is. And given that table that we had in a few lectures ago, or a lecture ago, is A times rad 3 equals 100 divided by rad 3. And I know that A is equal to 100 over rad 3 multiplied by rad 3 on top and bottom. And I get 100 rad 3 over 3. That is what A equals. So I found one portion of it. I found one portion. Now I need to find the other portion, B. And of course, to find B, I need to look at the other. I need to look at the other equation, the other right triangle. So what is this right triangle here? So this is the angle 30. Opposite is 100, and the adjacent is B as well. So I guess tangent again sounds like a good idea. So what is tangent? Tangent of 30 degrees in this case. 30 degrees is equal to 100 over B. So multiply by B on both sides, and I get the B's will cancel, and this becomes what? B times tangent of 30 degrees equals 100. We should know also what tangent of 30 degrees is, and it's going to be B times rad 3 over 3. That equals 100. Multiply both sides by 3 over rad 3 by 3 over rad 3, right? And now these here cancel with the fraction there, and I get 300 over rad 3 multiplied by rad 3 over rad 3, and I get 300 rad 3 over 3. 3 goes into 300 100 times, so we get 100 rad 3. So B is equal to 100 rad 3. So I know what A and B are individually, which means I know what X is. So now that I know X here, what is X? X is equal to 100 rad 3 over 3 plus 100 rad 3. What do I have here? I have two things that I can combine together if I have the same rate of denominator. So this, I'm going to rewrite it as 100 rad 3 over 3 plus 300 rad 3 over 3. Same denominators, combine the numerators. So I have 100 rad 3 plus 300 rad 3. It's a total of 400 rad 3 over 3. And that is the final answer here. Does 3 and rad 3 cancel? No. I mean, they don't cancel out. You can reduce it, but they don't cancel out. And what part are you asking about rad 3? At the end, rad 3 over 3, that you should just leave it as rad 3 over 3. 100 rad 3 times 3. Oh yeah, so this, why did I do this? Because I had this originally, right? And what I'm trying to do is I'm trying to combine these two quantities together. It's just that because these two quantities have different denominators, I can't combine them. So this is like saying, really, this is like saying 100 rad 3 over 1. And I'm multiplying this by the common factor of the least common denominator, 3. That's why I'm multiplying 3 over 3. And then because of that, I combine this here. 100 rad 3 times 3 is 300 rad 3 over 3. Same denominator, combine the numerators. 100 rad 3 with 300 rad 3 is 400 rad 3 over 3. Oh, you thought that rad 3 times 3 is 1? That's what you thought? That's not correct. So rad 3 multiplied by rad 3, for example, is 3. Rad 3 over rad 3 is 1, because anything divided by itself is 1. 3 over rad 3 is rad 3. I know there's a lot of things here. Remember rad 3 can be rewritten as 3 to the 1/2 power. So if you don't see that, this could be 3 over 3 to the 1/2 power. Same base, subtract the exponents. So it's 3 to the 1 minus a half, which is 3 to the 1/2, which is rad 3. Okay, so just remember that rad 3 is 3 to the 1/2 power. So you can't multiply rad 3 with 3 and get 1. That wouldn't make sense. Rad 3 times 3 is like saying 3 to the 1/2 power times 3 to the first power. Add the exponents. This is like saying 3 to the 3 halves. You see, all this stuff with the algebra and the radicals, it comes back to haunt you, right? So make sure you have that understood with the radicals. Okay, and let's do one more of these, and then we'll move on from all of this. So there's one more that I want to just show you guys. So we have another one of these kind of things where we have two right triangles. Well, we have one right triangle, but we have more than one triangle. So this angle here is 60 degrees. This angle here is 30 degrees. And this is 85. And what I'm interested in is this x. So I want to find x. Now, how do I find such a side here? How do I find it? So I have this right triangle here, right? I got one right triangle. I got this obtuse angle here, this obtuse triangle here, because this angle here is obtuse, it's 120. And if you notice, I also have this big right triangle here. And again, I want to find x. Now, this idea of using trig is particularly useful when you have right triangles. So again, this will be a multi-step process, because what I could do to find x, to find this side here, what I could do is figure out the bigger side, find this smaller portion, and subtract the big side with the small side here to find, and that difference would give you what x is. So we can do the a and b thing here. So call this A here and call this entire thing B. So what is X? X is really B minus A. Find B, subtract with A, and you get X. So let's find B first. So what is B? Look at the big triangle. Again, we get what? We get that tangent of 30 degrees is equal to 85 over B, because that's the opposite over the adjacent side. Find what B is, multiply by B on both sides. The B's here cancel, and I'm left with B times tangent of 30 degrees. That equals 85. Tangent 30 degrees, we just wrote that. It's rad 3 over 3. That equals 85. But I want to get rad 3 over 3 on the other side. So what do? I multiply by the reciprocal. That's how we get rid of the fractions. We multiply by reciprocals. So these cancel here, and I'm left with B is equal to 85 times 3 rad 3, but 3 over rad 3, like we saw here, like we just saw, 3 over rad 3 is rad 3. So 3 divided by rad 3 is rad 3. So I can go straight into this. And I know this is going to be 85 rad 3. That's I know for a fact that's what B is. Now, find A. How do you find A? Well, A value is here. This is the opposite side to 60. So I can use what? I can use tangent of 60 degrees is equal to 85 over A, and do the same exact thing again. Find A by multiplying by A on both sides here. And then the A's here cancel. And I'm left with A multiplied by tangent of 60 degrees is equal to 85. Tangent of 60 degrees is rad 3 equals 85. Divide that by rad 3 over rad 3. Cancel. And I get that A is equal to 85 over rad 3. Rationalize it by multiplying by rad 3 over 3. And I get 85 rad 3 over 3. 85 rad 3 over 3. Hold on one second, guys. All right, guys. 85 rad 3 over 3. Sorry about that. That's going to be 85. That's going to be what A is. So once I know what A is and what B is, I can find what X is, right? X is B minus A. So X is equal to 85 rad 3 over 3 minus, pardon me, that's A. So it's going to be 85 rad 3 minus 85 rad 3 over 3. And then to make them the same denominator, multiply top and bottom by 3 over 3. And then I get what? I get 3 times 85, which is 255. So this equals 255 rad 3 minus 85 rad 3. And all of this is being divided by 3. So then you could do 255 minus 85, which is 170. So X is equal to 170 rad 3 over 3. So the hardest part here is to know what to do, know what steps to get X, right? And that comes from understanding the triangles that you're given and knowing what trig ratios to use to find those missing sides. And once you're able to find those missing sides, you see the way you can combine them to get the missing side X. So there's a lot of problem solving here that's involved. Okay. Okay, so it looks like we may start with the trig graphs next time. Because we only have 20 or so minutes left. So now that we have more understanding of how to utilize, now that we know how to utilize these trig ratios to find these missing sides, we can do, for example, the following. These are like applications, right? Applications of trig. So we're going to be dealing with what are called angle of elevation and angle of depression. So for our first example, so if you are 1 mile away from the base of the Empire State Building, an angle of elevation of 11 degrees is made. And then it says use this information to find the height of the building. And for our sake, we're going to find the height of the building in feet. So we're going to have to do some conversion eventually. Oh, Tiffany, yeah. So I know someone's going to ask that, right? Can we just use the square roots and put it in our calculator, and all of this would just go away, right? All of this additional calculation will go away. So if the answer asks you to write your answer in nearest decimal form, then of course using your calculator would be it. But if it asks you to do in exact form, this would be exact. The calculator will not give you the exact value. So you could calculate it. You can literally just say, hey, your calculator does 85 rad 3, subtract that with 85 rad 3 over 3 in your calculator, and you're good to go. But this kind of calculation, right, with the radicals, right, this is something that you should be able to do as well. Should be. And it's really just algebra. From this point here, this is algebra. It's not something different in pre-calculus. It's just an algebraic manipulation and rewriting it as a single fraction. So what's the idea here? A lot of these kind of problems require you to envision it, to draw it, right? So we all know the Empire State Building. Right? I'm not an artiste, but this is the Empire State Building, right? And it says that if you're a mile away from it, so let's say we're a mile away. Let's say we're the observer here, and we're a mile away from the base of the Empire State Building. The angle of elevation to the, I should have mentioned to the top. So what I mean by that is that if I draw a right triangle to the top of this, right? And I try to just assume that this is like the bottom of the floor, the bottom of the ground level. Then you notice here, I have this right triangle, right? Where one side is a mile. This angle here is 11 degrees. And this height, I can call it x. X is the height of Empire State Building. So you see how cool this is? Instead of actually going to the height of the Empire State Building and then getting a really long ruler or whatever to measure the highest point to the bottom, I don't need to do that. I can literally just figure out what angle is made with my observation. Like, so then, okay, one thing I had to mention is like this is the eye. Okay, I'm not a good drawer. Okay, just to let you guys know. But if you're the observer and our line of sight, right, is 0 degrees here, then when you look up, sorry about that, guys. When you look up, you have what's called an angle of elevation. And when you look down, you have what's called the angle of depression. So what we're saying is that the angle of elevation made with the observer to the top of the building is 11 degrees from the 0 degree mark, right? This 0 degree mark is parallel to the ground. So if you just look straight ahead, parallel to the ground, right? That's your normal measure, right? Or the standard way that we view things, right? We view things from 0 degree straight ahead, just looking straight ahead. But then when we look up, we have an angle that's made between that straight level, right, to the top, which is 11 degrees. And once we have this, we have a typical right triangle whose angle is 11 degrees, whose adjacent side is 1 mile, and whose opposite side is the height of the building. So then what do we say? Tangent of 11 degrees is opposite over adjacent. And x over 1 is just x. So the height is just simply what? Tangent of 11 degrees. And what is tangent of 11 degrees? So you can go into your calculator. Make sure your mode is in degrees, not radians. Let me share that with you. And then I go to tangent of 11. And I get 0.194, 0.19438. So that's my answer. The height of the building, of the Empire State Building, given this information, is approximately 0.19438. But just make sure you remember what is the units. The units here are miles. So we have 0.19 miles. That's how high up the approximately the Empire State Building is. But let's say I want to convert this to feet. Does anybody know how to convert miles to feet? Or does anybody know the conversion between miles and feet? How many feet are there in 1 mile? Very good, Chen. That's right. So the conversion, 1 mile, is equal to 5,280 feet. So to find out how many feet there are in 0.19438 miles, just multiply this number by 5,280 feet. That's my conversion. So then when you multiply it out, what do you get? So I do 0.19438 multiplied by 5,280. And I get 1,026.33. I rounded to the nearest hundredth, so 0.3 feet. So in conclusion, the height of the Empire State Building is approximately 1,026 feet high. And of course, this is just a rough approximation. If you actually, yeah, 1,03624, right? 36. Oh, 36. Did I? Yeah, I got 3,264. That's why I rounded. But again, this is just approximation because I multiplied 0.19438 and I multiply that with 5,280 and I got 1,026.3264. That's what I got. But look, the moment I did this, right, the moment I truncated, I took a portion of the decimal expansion of tangent of 11 because tangent of 11 continues on. But I only took these numbers and thought this was enough. The moment I did that, I already lost accuracy. You understand? So that's why the approximated value should be done at the end. When you want to find the value, you should do it at the end, not during your calculations, because if you could use this during your calculations, the approximations, and it will just veer you away farther away from the actual correct answer. But regardless, let's see the actual height of Empire State Building. So yeah, we're kind of off quite a amount. It's 1,457 feet. So just quite a discrepancy. Again, this is a word problem that you find sometimes. It's not completely accurate, 100%, but the idea is there. The idea is that you can find the height of a triangle of an object or a structure without actually having to find the height directly. You can find it indirectly using trig if I know other pieces of information. Okay. All right, let's do one more of these, but now we're gonna do with angle of depression. So in this one, we have from the top of a lighthouse, from the top of a 200-foot lighthouse, the angle of depression to a ship in the ocean is 20 degrees. Sorry, 23 degrees. How far is the ship from the base of the lighthouse. So then I draw, right? So I create this lighthouse. Again, I'm definitely not a good artiste here. But here we have a lighthouse. And we know it's gonna be, we know the height is 200 feet. And then if I'm up here, right? If I'm an observer up above and I see in the ocean out here a ship, right? And the angle that's made, so this is gonna be my line of sight is if I view it parallel to the ground, this is eye level, right? Eye level. And eye level is parallel to the ground. If I make an angle of depression and I see the ship, this is going to be 23 degrees below eye level, right? And I want to figure out I create this right triangle because I want to figure out what is the distance from the ship to the base of the lighthouse, knowing that the side here is 200. You see this? You see how I simplified this physical situation with a right triangle? And I know this is 23 degrees. So there's many things I can do here. If I know this is 23 degrees and this is parallel to this, then if I draw a straight line down, this would be a 90-degree angle. So I would do 23 minus 90. And that would be what? 67 degrees. So this angle here would be 67 degrees. I can view it that way. Or if I know about a little bit more about geometry, if I know this side here is parallel to this side here, then this angle here these angles here are called alternate interior angles, and they're the same, 23 degrees. So it's up to you whether you use this angle here, 67, or if you use this angle here, 23 degrees. It's up to you. You still get the same answer. I'm going to use 67 degrees. Why am I going to use 67 degrees? Because this is my opposite side. This is my adjacent side. So I know this is tangent of 67 degrees is equal to the opposite side x over the adjacent side 200. Multiply by 200, multiply by 200. 200s cancel, and x is equal to 200 tangent of 67 degrees. And so I can figure that out. So just use your calculator now. And then plug in 200 multiplied by tangent of 67 degrees. Make sure you're in degrees. And I get 471. 471.17. I'm going to round it to the nearest hundredth. And so then I say that the ship is roughly 471 feet away from the base of the lighthouse. All right, so I hope you start to see how essential or useful trig can be with solving these kind of problems. For some reason, I did what you did, but my answer was not the same. So let's see. Are you in the same, are you in degree mode or in radian mode? So that's important. So let me see if I'm in the correct mode as well. I am in degree mode. So then when I did 200 times tangent of 67, I got 471. So be careful with how you plug it in your calculator. Yeah, make sure you're in the right mode. So that's gonna be the biggest thing with trig from now on and using your calculator is what mode you're in. So if you're using angles, then use if you're using degrees for your angles, then make sure you're in degree mode. If it's in radians, make sure you're in radian mode because it gives you completely two different answers. Because if you do the radians, the calculator interprets 67 not as degrees, even though you think it's degrees, it would interpret it as radians. And 67 radians is not the same as 67 degrees, obviously. So that's why you get two different answers. So make sure you use the correct degree in your calculator when you use it. So I'll finish up a bit earlier here. Next time we'll have a quiz and